Welcome to Python tutorial 5 of the course Time Dependent Quantum Chemistry. In this tutorial, we will go over the one-dimensional Wavepacket dynamics, which will be solved numerically. So this is the ultimate motivation we had in this course. Systematically, we have learned how to what does it mean by Python programming. We have presented that. Then we have presented how to get the expectation value, how to normalize a discretized wave function. Then we have checked how to get the eigenstate and eigen values associated with a particular system or Hamiltonian. And this is the ultimate motivation where we would like to take a look at how the wave packet can propagate in time, particularly one-dimensional wave packet propagate in time numerically, so that any potential can be used to check the propagation. We have already outlined the split operator approach to solve the TDSE, and we will see the numerical implementation of in Python programming for this split operator approach to propagate that one. So the aim is following. We may have a potential like this. This is, let's say, potential, and this is the x-axis, and this is Vx. And I may create a wave packet here. When I'm creating wave packet and drawing wave packet like this way through this envelope function, I'm not just showing the entire wave packet. The actual wave packet looks like this. There is an oscillatory part in addition to this envelope function. But to reduce the complexity, we just simply use this the envelope function to show the wave packet. So the wave packet has been created, let's say, at this initial position x naught, and it should propagate now. And if it is propagating, when it's propagating, it will experience a potential. So it may so happen that if this is the potential I have, so in chemistry we talk about the reactant, and on this side you have the product. That's all about the simplest form of the chemical reaction. Reactant is converting to product, and when reactant is converting to product, there is a Wavepacket dynamics going on the potential energy surface. And if we know the dynamics, if we know the time scale of this propagation, we know the dynamics of this reaction, this reactant converting to product. So Wavepacket dynamics constitute the very basic quantum dynamics in chemistry, and it is very easy to understand also. We know that wave packet analytically we have solved it. When the wave packet propagates, it will spread out and it will decrease the amplitude in general. That's the basic idea, but it is not true always. If the wave packet has been created in the harmonic potential, so what happens in the harmonic potential? It is a narrow wave packet we create, then it forms, it spreads out in the middle, and then again it becomes narrow. So the exact nature of wave packet and its dynamics depends on what kind of potential it's experiencing. But mostly wave packet, when it be propagating, it will be spreading out. And when, let's say, when wave packet is propagating in time, this is time axis, wave packet is propagating in time, is spreading out, it doesn't mean that the particle size was previously very narrow and now it's spreading out. It is not representing the particle size. Particle itself is a quantum particle. Quantum particle is a very tiny little particle. It is a point particle. But the problem is that its exact position I cannot determine. It is just what will happen, that I will have a distribution. So single experiment can give me one experiment, one exact, one tiny, point position. But if you repeat the experiment, we'll see that we'll have a position distribution. So this is the distribution function which is evolving as a function of time. That's the meaning. We should never say that, okay, size of the particle looks like a camel. Let's say this size looks like a camel, and this camel is converted to let's say a dinosaur. It's not like that. The size of the particle does not change. Size of the particle remains to be the tiny little particle. That's why quantum effect is showing up. It is a point particle, but its distribution function is going to spread out. That's the meaning of it. And so this is something which you should remember. Another thing is that when Wavepacket, let's say a flight. Let's say a flight, if I have a mountain here and a flight is flying over the mountain. When a flight is flying over the mountain, it can reach from point A to point B. That's the classical picture. It can reach from point A to point B, from let's say Bangalore to Kochi or Delhi. It can reach there with 100% probability, as long as it is above this barrier of the mountain. But whenever we think about the quantum dynamics, you look at this particle is actually having energy above this barrier, and when it's moving, classically we'd say that, okay, 100% this entire probability will come down here. But that doesn't happen because of this barrier, existence of this barrier here. Always there will be a scattering at this point. Even if it is above the barrier, it will have a scattering. There is a probability of the wave packet going back, and there is a probability of wave packet moving forward, always. And that limits the percent yield or the kinetics or dynamics of the entire chemical process. So we should always remember this one. This is something which will be, if time permits, we'll study it in the quantum scattering part. This is so quantum scattering is an important subject in chemical reactivity, and we study that one. And it suggests that as a very unusual outcome of quantum scattering, even if the particle is above the barrier, it will be scattered because of the presence of this barrier. The barrier is present, and that's why it will be scattered. And to what percentage will be scattered, that depends on where you are with respect to the barrier. But there will be a scattering. And if there is a scattering, there is no chance of 100% probability transmission here. So product formation is limited by the barrier and where you are. So this is something which you should keep it in mind, and these are the effects like quantum scattering effects and all these things we can understand better with the help of this Wavepacket dynamics. So this contradictory picture should be kept in your mind always, that classical particle can transmit the barrier, can go over the barrier with 100% probability, but quantum particle, when it's going even over the barrier, it cannot transfer the probability 100%. Always there will be a scattering, and a percentage will be reflected back. Okay. So with this, and the question is why we need numerical methods. We have used analytical approach for Wavepacket dynamics. Wavepacket dynamics, we have seen analytical approach, and we have seen that it works for zero interaction potential when the particle is not experiencing the potential. It works for linear potential when the particle is experiencing linear potential, and it works for analytical approach works for when you have this exponent the quadratic potential. So these are the three situations where analytical approach works, and we can solve it analytically. But if we go beyond this quadratic potential or linear potential or this zero potential, you need to solve it numerically. And these are the case very in practical situation we do not get this linear potential, we do not get this quadratic potential even. In practical scenario, my potential may have this kind of potential, and there is neither linear potential nor this quadratic potential. We have to create our own potential, and based on that potential we have to propagate. And in that case we need the numerical solution to this Wavepacket dynamics. So numerical solution to this Wavepacket dynamics is very important for practical application, and we'll go over it. Parts of the techniques we are going to use for this entire Wavepacket dynamics, that part of those techniques we have already gone over: Fourier transform, then normalization. We'll just integrate them and then we'll come up with the solution. So we'll make use of, as I've told earlier, that we are going to make use of split operator approach in this numerical problem. And conceptually the probability of finding the particle at any given position and time is determined by the square of absolute value of the wave function. So if I have a wave function like this, then the probability of finding the particle, this gives you, quantum mechanics always gives the probabilistic answer to the question where is the particle, and it gives the probability. So if psi xt is the wave function, then the probability function becomes psi xt absolute square of the absolute value of the wave function. So this is something which we have understood in this course, as we did before during the translational motion, discussion of translational motion. Let us assume that the initial wave function, so the entire Wavepacket dynamics is based on the or any quantum dynamics is based on few steps. The steps is that we have to construct the initial wave function. That's the initial gauge we have to make. And what kind of initial gauge, how to make a good initial gauge, that depends on our understanding of the experimental condition, because the particle, how it's starting its evolution, that has to be decided based on the experimental condition. And that's why we need to understand the experiment or experimental condition very well, so that we can come up with a proper initial wave function representing the system or representing the particle. But here we will assume that at t equals 0 initial time, I have the wave function like this. This is called propagating wave function, propagating Gaussian wave function. So we have seen that this is called propagating Gaussian wave packet. So this part is responsible for the propagation and this part is responsible for the envelope. So this fast varying component is represented by e to the power I k naught x, and this part, envelope function, blue part, is given by e to the power minus a x square. These are the two components we have, and this is normalized. As we see, it is normalized, and that is the another requirement. We have to always begin with normalized wave function and then go for the solution. Good thing about TDSE is that it preserves norm of the wave function. So normalization is not time dependent anymore. Normalization will be constant, and that's good thing. because every time we have to confirm that at any given time the total probability of finding the particle from minus infinity to plus infinity has to be 1, because I have single particle which is moving. So that this is the only interpretation of quantum mechanics through this probabilistic idea. Now so this is our initial wave function. That's the assumption we have made, and we know that this k naught is going to, this is a real constant representing the angular wave number of the carrier wave of the wave packet. These are the meaning of this angular wave number is now clear to us. In two different contexts we have presented it. In Fourier transform we have presented it, and also in the context of translational motion we have presented it. And we have also understood that this k naught, the moment this is x domain representation of the wave packet. If we do the Fourier transform, we get another because it is a Gaussian shape in the x domain. So in the k domain, Fourier domain, we also get a Gaussian, and the center of the Gaussian is actually represented by k naught. So all these consequences and features of a wave packet is known to us already based on the Fourier transform discussion we had previously. And also we know that the this k naught is actually defining the velocity of the particle. This is defining the velocity of the particle. So k naught has multiple perspective. Okay, it is defining that velocity of the particle. It is defining momentum of the particle. It is defining the center of the spectrum, this momentum domain spectrum. It is so k naught has many perspective, and those perspectives should be clear to us before we go for, or before we make use of this wave function for our wave packet dynamics. And another thing we remind here, that the way we have taken this function, this envelope function e to the power minus a x square, we know that this function is centered at x equals 0. That we know. So e to the power minus a x minus x naught whole square, this is centered at x equals x naught. But if I don't have x naught, then it is centered at x equals 0. So this is something we should remember, that we are starting with a wave packet which is centered at x equals 0, and we'll see how it's evolving. Now, question in this entire problem is that how do we explore the wave function numerically given the initial wave function So the question is, how do we explore psi x? And analytically we have seen that this is an analytical approach we previously used, and we have seen that this is the wave packet we get, and finally we have got this integration done, and one final wave packet expression we have been able to produce in the earlier one of the modules. What we are going to do is that we are going to do the same thing numerically, and we can check what we previously got analytically and how does it compare with the numerical solution. So in order to do this, if we now jump into the numerical problem, it is clear that we are going to use this t equals 0 time. At t equals 0 time, we are going to use this wave function, and the first step of this entire procedure is to normalize the wave function. So first we will check how to normalize the wave function. This is quite clear to us now. I will move to laptop and we will write down the initial wave function as follows. First, we will be importing certain modules and submodules for our work, importing the required library from SciPy import. We will import square root functionality, arrange functionality, and exponential functionality from SciPy dot integrate. This procedure is quite similar to what we did to find out the normalized wave function in Python tutorial 2, and that's the procedure. So we are, because we are familiar with it, and that's the reason why I can directly write down what I need to import. So from SciPy integrate, I have to import Simpson's method, because I have to do this integration, numerical integration through Simpson's method. From matplot library pyplot, I will import plot, xlimit, and show. All these features are known to you now. Now I'll be first creating the x grid. When I first create the x grid, I will write out x minimum equals minus 1000, x maximum equals plus 1000, plus 1000.2 I'll write down, because this point will be excluded from the list prepared by the arrange functionality, and then dx I will place 0.2. So this will create the x domain, and then I will define x equals a range functionality, x minimum, x maximum, and dx. So this will create the array. Now I'll be able to define and normalize the initial wave function. Good command line will help you remember what you are doing right now, because it's very easy to forget this programming unless you do the practice regularly. Exponential of minus x square, I will make minus x square by 2. It's just, that's the way I am selecting. It doesn't need to be like that. Anything you can select, as long as it is a Gaussian envelope, it's perfectly fine. And then this propagating part, which is 1j, we know that the complex number is written in Python as j, then k naught, then multiplied by x. Now x is actually t. This is x domain. Yeah, this is x domain. And so once we have defined this one, this definition we can write down. This is a traveling Gaussian form. Then we have to find out the probability density. Probability density would be given by absolute value of psi. This is the probability density. Then I can find out norm. Norm equals Simpson's method, y, this y and x I have to give, and y is going to be the probability density, comma, x. So it will be sampled on each point of x, and it will be done, it will be the numerical integration will be done. Numerical integration in the end giving you the area under the curve, and finally I will be plotting this PSI PSI norm I am getting as the wave function divided by the norm divided by SQRT of the norm. That's the definition of, that's the way you normalize the wave function. So this is the way we have done it, and as we can see that this plotting part we can avoid right now. We can just check whether what we get from here, and this is the way it can normalize it. So I can write down print norm So if we run the program, we see that it is printing the value, the norm. It has given 1.77 value, and it can be assumed that, and I can also plot if we want to check the wave function which we are dealing with. So in that case, I need this matplot library.py plot. We have to use plot, show, x limit. These are the things we need. So we can plot even plot PSI norm, comma, this is x, comma, this part is x, comma, PSI norm. So I'll remind this also, I have reminded before, but I can remind again. See, when you use Simpson's method, you write y value first and then x value, but when you use plot, you write x value first and then y value. So y array, these are all array. So that's the way it does, and the syntaxes are. So I can again run the program, and I can see that it can be plotted as this, and we have we can make the we can do one thing. We can change the x limit. We can control the x limit as let's say -5 to +5. Let's see what happens if we use -5 to +5. Yeah, this is the wave packet we have right now, which is having an oscillation, and if you forget that oscillation, it is going to give you the envelope function. So this is all we have. The initial wave function we have defined already, and we can see that it is centered at 0, which is x equals 0 position. So these are the points we have found from this. So now we will go back to the discussion here. What we have done in this is that the momentum of the free particle, if we look at the momentum of the free particle, momentum of the particle, that is going to be h cut k naught. That's the momentum we get. All these calculations in general we do in atomic unit. It is an unit system, which is very frequently used in calculation of atoms and molecules, electronic structure calculations of atoms and molecules, and then Wavepacket Dynamics. All these calculations are used based on atomic unit. Under the atomic unit, there are certain things we assume or we consider. Under atomic unit, H cut is considered to be one atomic unit, and in that case, momentum we get as k naught in atomic unit. So when I say momentum equals k naught, in atomic unit it is k naught. Now, if the particle is considered to be an electron, if we consider the particle is an electron, in that case, this momentum will be represented by this k naught, and me is considered to be, again in atomic unit, mass of the electron is considered to be 1 atomic unit. In that case, velocity is equal to k naught. That's the this is in atomic unit only. So when I have considered in this numerical procedure, I have considered here. I have considered. You can see that this k naught we have considered to be 1. It means that I have considered velocity of the particle. So the particle is considered to be electron and velocity equals k naught equals 1 in atomic unit, and it means that it is 1 atomic unit of velocity. So what is the velocity with which the particle electron is traveling in my problem? In this problem, we are assuming that the particle is traveling, initial velocity was 1 atomic unit, which is equivalent to, I mean, 1 atomic unit may not make sense to you, but which is equivalent to, in the SI unit, if we write down, it is going to be 2.188 into 10 to the power 6 meter per second. This is the SI unit equivalent, SI unit component, SI unit value. So we are assuming that particle is traveling with this velocity. So what is the idea of atomic unit? Atomic unit was proposed by Hartree in the beginning of the, when the quantum mechanics was being proposed. Hartree actually came up with this idea that we should use atomic unit in these calculations, because we are going to deal with very large number or very small number. Sometimes we may deal with -10, this kind of number, or sometimes we can deal with this kind of large number. And in order to use this kind of large number, it is going to be very difficult to use the SI unit for this calculation. It will be much convenient to do with this atomic unit, and slowly entire quantum mechanics community has accepted that yes, it is the convenient way to go ahead. So when I have written here x maximum, x minimum, that 1000 and 1000.2, it is assuming the atomic unit of length. So when I say that the wave packet is centered at 0, that is 0 atomic unit of length. If the wave packet has moved from 0 to some other value, let's say 10, then this is the 10 atomic unit of length. Everything has been represented in the atomic unit, and based on this representation only, if I think about the kinetic energy of the particle, kinetic energy of the particle is going to be half me. We are considering electron as a particle, half me, and then v square, which is nothing but half me is 1 and v equals k, which is k naught square. So half k naught square is the kinetic energy of the particle in atomic unit. So as you can already realize that if we use an atomic unit, many factors is being simplified if we use the atomic unit. So that's the basic idea. Remaining part, whatever we have written in the program, is equivalent to the way we have learned the normalization thing, how to normalize a discretized wave function. So this is a discretized wave function representation, and we are normalizing it. So first thing we have to do is we have to normalize the wave function and initial wave function, and then we have to propagate the initial wave function. The propagation part we will look at in the next session.